Welcome to Pryor's Lab. Today I want to show you a little teardown of a Stirling-based thermal imaging camera. When I watched some teardowns on YouTube, there were especially two ones which were very interesting about similar thermal imaging systems. These were the ones from Mike's Electric Stuff, and the other one from Tesla 500, and they both tore down a Vidicon-based thermal imaging system. So it's not exactly the same. I think the Vidicon-based system is quite a few years older than this one, but the Stirling-cooled or cryo-cooled focal plane array system is also rather obsolete these days. On the front you can see the lens, 50mm in this model. It's a germanium lens. This unit came with two lenses, the 50mm focal length lens attached to the unit, and this one. That's a 100mm germanium-based thermal lens. A really great thing. It's a pity they didn't include the wide-angle lens, which exists too. It's a 25mm lens, which would be much more usable in daily use. On the side of the unit you have only two control switches. One is for brightness and the other one is for contrast. Here you have a LEMO connector for the little screen attached to the unit. There you can see the OSD and the thermal image, of course. In the original version there was a viewfinder, black and white, like on the old Sony studio cameras. But I didn't like that because I wanted color screen, and there was a problem with this CRT-based black and white viewfinder, so I removed it and attached this color LCD screen. On the back you have several connectors. Here on top, that's the digital interface for different acquisition systems which were sold separately for this camera, and calibration systems for uniformity correction of the sensor and stuff like that. You have a switch to select between NTSC, or in this version PAL, output, and VGA, so you can connect, you can connect VGA 640x480 VGA monitor directly here, or you can select PAL or NTSC and get on this connector a normal composite video output. With a second switch you can choose between corrected output and uncorrected output. This belongs to stuff like the uniformity correction and temperature correction for thermal readouts. Here's the power switch, power LED, and another control for different color palettes like false colors and black and white, inverse black and white, and isotherm lines within the picture. Here you can select the legend you want to see in the OSD, and of course a LEMO power connector. Again, very high quality power connectors. This LEMO stuff is really good. On the front of the camera you have the germanium lens, and beneath that you can see a glass assembly here in the middle. That's a glass assembly which is evacuated. There is a little tube in the middle, and below that perhaps you can see it in the middle, the focal plane array itself. Here in the reflections you can see it a little bit. That's mounted on the so-called cold finger of the Stirling cooler to create cryogenic temperatures to cool the sensor down for correct measurements. I'll show you that in a minute on the block diagram of the camera. So let's crack it open. I've removed all the screws, because that's the boring part. And when you remove this cover, let's first take a look at this. As you can see, this whole assembly, the side assembly, is milled of a full aluminium block. It's not molded, it's milled of solid aluminium. So I think this entire assembly, this entire camera system, surely wasn't made on a budget. So it may really have cost a fortune back in these days. I think it's clearly visible that it's a military style manufacturer. This is very rugged and heavy stuff. Very great metalwork. So again, piece of foam for thermal insulation and protection of the inlays. And that's the inside of the camera. Here in front you can see again the glass chamber with the focal plane array inside. This is the flex ribbon cable connected to the focal plane array and going up here to our board 1. This is board 2 and this would be board 3. Back here is a little backplane connecting all those boards together. Down here is a heatsink with a little fan. This is actually connected to the Stirling cooler unit itself, which generates the cryogenic temperatures for the focal plane array sensor. Here is a little DC-DC converter, nothing special, nothing fancy. There are many companies building stuff like that. And the somewhat messy output here with some heat shrunk assemblies and a fuse holder inside here just hanging around. Yeah, many cables down here. So I think the whole unit is very a great build technology. They made many efforts to do a really good design, good job. But the back panel here, these connectors, yeah, okay, I don't know, I don't like it that much. Here at the back, you'll see later, there's one 3-pin connector. There's no locking mechanism, so I don't know what would happen if you expose this thing to vibration tests or something like that. So the rest of the unit is really great manufacturing, but the back plane here, I don't know. So let's continue. I'll remove the other cover and then the card cage and show you that next. Let's remove the right cover of the camera. Again, you can see the completely milled assembly here with the rocker switches right here and the handlebar. And again, there's a lot of thermal insulation material inside the camera. Let's put this just over here. On this side, the first thing you can see is this little bulge board. And actually that was done by me a few years ago. I needed to use the camera, and the 4.43 MHz PAL color subcarrier crystal didn't oscillate anymore, so I had to do a quick hack with stuff I had laying around to bring the camera back to work. And as you know, these temporary fixes, yeah, they tend to they tend to last very long. So it's still inside there and still working, and I think I won't bother anymore. It's working and it's okay. So back again here, board 1, 2, 3, a little bulge board by me, the backside of the DC-DC converter block here, the fan, and this is the Stirling cooler itself, the hot end of the Stirling cooler. So within this unit, there is the piston transferring the heat from within the evacuate chamber here, from the cold finger with the focal plane array, into this assembly and radiating it with these fins here to the air. Here you can see the temperature sensing wires. I think these are Kelvin wires with a very special insulation and special material for thermocouple voltages. This is the 24-volt rail for the Stirling cooler itself. So the Stirling cooler assembly is completely autonomous. There's no control connection up to these boards. It's just connected with a thermal sensor into the evacuated chamber, and it gets the 24 volts on this rail here. So let's continue. A really cool thing about this unit is that I got the original user's manual from the manufacturer. So when I got the camera from eBay, I didn't know anything about this thing. It was just sold as broken thermal imaging system, and they didn't know anything about it. They just sold it for a bargain price. So I got the unit, and the only hint for a manufacturer is on top of this lens. So perhaps you can see it. Cincinnati Electronics. Nothing else. There's no type shield anywhere on the machine, no manufacturer sign, nothing. So I went to the internet and googled for Cincinnati Electronics, and they still exist and manufacture weird military stuff in America. So I thought, come on, let's give it a try. I took a picture of the camera and sent them an email and asked for any information about this device. And believe it or not, a few days later, I got this scanned PDF document with the entire user manual and specification for this camera. Really great company. If you ever need weird military stuff, buy it there. I like them. Let's go a little bit through the user's manual of this device. It's the IRC-160ST I've got. 160 because it's 160 by 128 pixels on the sensor. There's the ST version, which stands for Stirling cooled, and the non-ST version. The difference is this version with ST, the one I have, is including a Stirling cooler to reach the cryogenic temperatures on the focal plane array, whilst the other version has a DUR and you have to fill in liquid nitrogen to cool it down. So this one is a lot more handy. On this picture you can see both versions. This is the one I have, and you can, yeah, you can't really see it, it's a bad picture, but that's the original viewfinder which was attached to the unit. Or I'll have a look in the basement, perhaps I still got it, I don't know. I have to look it up, it's only black and white and I didn't really want to use it. So that's the camera you saw before, and that's the version with the DUR, so you can open this port on top here to fill in the liquid nitrogen. It's really hilarious. The whole manual is full with warnings and hints how to use the device, and they, of course, if you have the DUR version, you have to pour in liquid nitrogen at a temperature of minus 193 degrees Celsius or minus 321 degrees Fahrenheit. So it's really cold stuff, so you need to take special precautions when handling this thing. You need special clothes, special gloves to use, goggles, and the whole manual is full of hints and safety advices. Here they've included a nice block diagram for the camera and its usage. So the camera I got originally included this crappy old power supply I've thrown away the same moment I got it. I think it was broken and it was a really huge old unit. I think the whole camera system was manufactured in 1992. Or at least the manual revision is from 1992. And the power supply was really huge, old, non-efficient unit with, I think, about 12 volts, 3 amps. And I've removed the connector, the LEMO jack, and used my own ones. And didn't even bother to fix the power supply, because today it's ubiquitous to get a 12 volt power supply switch mode. You get it everywhere for nearly nothing. So you can connect here your VGA monitor, normal NTSC or PAL monitor, video cassette recorder. Back in these days that was state of the art. Let's come to the interesting parts. This manual contains the whole pinout of the external connections. So here on the bottom left, the VGA connector, the power connector, this is the Stirling, non-Stirling cooled version. Here the LEMO connector pinout diagram for my camera. And also the pinout for this external data connector. So you would really be able to make your own equipment to connect to the camera. It's great, and in these days I think they wouldn't include all these pinouts. So you can buy assemblies to connect to, but they wouldn't print that into the manual. I think they've gone through real effort to create this manual, and you'll see this on the next pages too. What I really like about this user's manual is that they've included the timing diagram for the external expansion port on the back of the camera. Let's go for a short moment through the pinout of this connector and its connections. So first we have a pin called sign here. I guess the sign might be for something like positive or negative temperatures, I don't know. So there's no specification on these pins. Perhaps I'll show you later some screenshots from my HP Agilent 54622 mixed signal oscilloscope, and I'll hook up all those digital probe pods to this bus. I've manufactured a little breakout connector for this to connect it to a PIC32 microcontroller to add some cursors and readouts. But I think I've never completed that project. I have the picture right there and it showed up on my OLED display, but I've never completed the whole thing because that's much more usable here these days. So if I want digital readout and accurate temperatures, calibrated values and storage to SD card, I take the more modern Trotec camera. So I didn't continue that project, but I managed to use this documentation to get a correct color picture on my 160 by 120 OLED screen on my PIC microcontroller, and I really like that. There's enough information within this data sheet here. So as I said, there's the sign output. there are some down and up offsets and the bad pixel input, so I don't really know what to do with these. But now there are the interesting pins. Here is the start of frame pin. Below there is the data ready and the 12 data bits. So with the timing chart back here, you can exactly see how to determine the beginning of a new frame and the transitions between different lines. So you can clock in every pixel into your memory on your microcontroller and process the data as you want. So you can manage to use different false color mappings or averaging between different frames, or what I've done, some kind of bad pixel hiding. So the camera has one problem: the sensor, you will see later when I power it on, has some hot pixels which are always white. So I've chosen a way in my controller to see whether all the pixels around the white one, which always reads very high value in temperature, are actually about the same value or quite lower. And if all around are quite lower, I presume that this one should be lower too. So I change the value of these stuck pixels, and you get a much nicer appearance on the screen. So I've just replaced these values with surrounding values, and it gave a much more uniform output on the screen. So I really like that, and I would really appreciate it if more manufacturers these days would go into the effort of including this information, because it's great afterwards. If your unit becomes older or is somewhat obsolete, there's still a base of people hacking around with it, so great thing. This is the complete block diagram of the entire camera system. As you saw before on the close-up of the camera, there are in the card cage 3 boards, 3 PCBs, and on the block diagram there are also these 3 boards, 1, 2 and 3. So let's start. On the top right there is our focal plane array. Let's zoom in a little bit. This is our temperature thermal sensor element, 160 by 128 pixels, and its output is somewhat like CCD sensor. It's pixel wise addressable and shifted out, and it's purely analog, the signal. So this analog signal goes on board 1 into a gain stage, they call it, and afterwards into analog primary gain correction and an analog primary offset correction. So these offsets and gains are factory adjusted during production and initial calibration of the camera system. The conditioned analog signal goes from board 1 to board 2, and here is our 12-bit AD converter and timing control. The digitalized signal goes into the secondary gain correction block and the secondary offset correction block. These are in fact 2 EEPROMs on the second board. You will see them in a minute. After that there is a global offset, a global gain correction, which is associated to our rocker switches to set brightness and contrast. In fact, I think there's a way to change the content of these EEPROMs by a user software via the expansion bus connector on the back of the camera. I found a document on the web mentioning a software where you could add your own calibration coefficients to these EEPROMs, but I couldn't find anywhere. So I think this was a highly specialized application where you could do this, and I couldn't find any way with a timing diagram attached in this manual to set them manually. So perhaps we'll remove the EEPROMs and have a look at them and see whether we can change anything. After these secondary corrections, there's our data port connected to the data here back at this point. There's our brightness control, as I said, and the contrast control, these 2 knobs on the side of the camera. The output of this board then goes to the board number 3, which is the video generation board. So here's the video timing control and the video frame buffer memory with a 10-bit palette for the color generation and stuff like that. On this page you can see the whole block diagram of the focal plane array itself. Here they say it's the thermal 160 by 120 pixels multiplexer, so I'm sorry, it's only 160 by 120, not 28, actually. So you see, the focal plane array works somewhat like more modern CCD sensors. You have a so-called slow shift register and a fast shift register. These are actually rows and columns. So you can address every pixel by a row and a column address, and the value of each pixel is shifted out as an analog signal. So there's an analog gain stage next to the focal plane array, and you only read analog values like in CCD technology. So let's remove the card cage from the camera. There are only 3 screws left. And after that one, we should be able to remove this whole assembly from the camera. So come out. It's stuck? No, it's not. So, it was the bulge holding it down. So here we have the card cage with the 3 boards. Let's zoom out a little bit. And I'll remove these bolts holding these boards together, plug out the boards, and show you them in a minute. This is the first of 3 boards, the board which takes the analog signal from the focal plane array. As a reference, I've put, again, the block diagram of this board beneath it. Let's zoom out a little bit. Here you can see it. So what do we expect from this board? We expect to see our analog input from the FPA. We expect to see the gain stage, some kind of correction for the gain, and multiplication stage, and some kind of offset correction and addition stage, and then analog output of this device. So with that knowledge, let's switch over to this board. I'll zoom in a bit. As you saw before, the card edge connector here is our connector to the focal plane array. Here our analog information comes in. So you can see it's a rather dense layout of the board without any bulges, by the way. So you can see where every signal is going here. But let's take a closer look at the different parts they used here. So here at the input we have an AD842. That's a fast operational amplifier. We have a precision reference with 5 volt. It's a LT1021/5. We have a precision 12-bit digital to analog converter. It's an AD668KQ from Analog Devices. And here we have another high-speed digital to analog 12-bit converter. This time it's an AD565 from Analog Devices too. So how does this whole unit work? I think the input signal is taken into a impedance conversion stage and buffered, and afterwards these different kinds of correction have to be applied. So how can they achieve this? I think their approach is to use these 2 precision digital to analog converters in conjunction with these EPROMs on this board. Or let's say PROMs. Actually, they aren't electronically erasable because they have these windows here. So I think during manufacturing process they take this board together with the focal plane array sensor in the particular camera, and they store the correct gain and offset correction values into these EPROMs. Into these PROMs. It's rather you don't use them these days, so it's normally I'm only working with EPROMs. They're storing the correction and gain coefficients here in these PROMs, and when every pixel is acquired here, the state machine consisting of these 47HC devices always exactly knows at which pixel it is at a certain time, so it can select the correct address in these PROMs and load the correction value stored during manufacturing process and convert this to analog with these 2 digital to analog converters, and then use all these operational amplifiers and buffers to apply the correction to the analog signals. So remember, the whole board here works in the analog domain. And I think here's the output side, here's a Zeppelin 12 amplifier, here's again a reference clock for the whole system, and some dip switches. So I don't know, there's no documentation what these are doing. Your guess is as good as mine. Here we have two optocouplers, 5 volt, 7805 regulators, so nothing fancy here. So let's continue to the next board. I'll show the backside too. So there's nothing interesting on the back side, just wires. Absolutely no parts. So let's continue with board number 2. Let's start again with the block diagram of board number 2. So what do we expect here? We have our input from board number 1, the analog pixel data, going into a 12-bit analog to digital converter on this board. And then in digital domain, there is again secondary gain correction, secondary offset correction, global offset, global gain. So remember, these two values come from our rocker switches, so we can adjust brightness, the global offset, and global gain, and contrast with these knobs on the camera housing. And we have these secondary offset correction and gain correction parameters we can enable and disable with a cal and uncal switch on the back of the camera. So let's take a closer look at board number 2. What do we expect to see here? We expect a processor, some more memory, and some user programmable memory. So here we in particular expect some EEPROMs. So let's take a look at this board. That's it. And in fact, you see what we expected. So what do we have here? This is our central processing unit. It's an ADSP 1101, very ancient DSP processor, date code 8943. So I guess this unit was manufactured in, let's say, early 90s or really 89. So it's very old stuff here. Let's look at the board again. Let me align this. Okay, here we have our cartridge connector. Here our signal is coming in. The digital to analog converter is here. It's an AD1671. It's a very weird angle to work here with the camera in front of me. This is the 12-bit analog to digital converter. Here we have our main program storage PROM, again with a glass window. Like I said, the DSP, some glue logic, 74HC, CMOS logic here. Here is a counter. It's a programmable logic device, a little one, very ancient one. I think this one controls the state machine for the pixel synchronization between the different boards to offload all that data from the DSP. And here are two EEPROMs. And I guess these two EEPROMs are the ones which store our secondary gain and offset correction coefficients, which can be adjusted from the outside. I think I'll prepare a nice little experiment. As the gain and offset correction with a switch on the backside of the unit doesn't work, we should be able to remove these two, read them out, and replace the values, let's say with zeros or every byte with 255. And let's see whether that changes anything on the output of the camera later on. Let's continue with the last board, the video output board. So what do we expect here? We have again on the right side in the block diagram our digital data input. So remember, here is 12-bit data coming in. We have a fit function. I presume the fit function means this unit is used to do the mapping from the 160 by 120 pixels of the focal plane array to either 640 to 480 VGA resolution or the appropriate PAL or NTSC video standard resolutions. So there's some mapping to another resolution, also still at 12 bits. And then this 12-bit signal in this frame buffer memory is taken into a 10-bit palette. So this is some kind of lookup memory for downsampling not the resolution, but the dynamic range of this data from 12-bit to 10-bit for the 10-bit RAM DAC video analog output driver. So we lose some data on the analog output. Remember, the only way to get the full dynamic range 12-bit data would be to use the expansion connector on the back of the camera. So let's take a look at the board. Here I put my little bulge out of the picture so you don't have to bother with it. Here we have our triple video digital to analog converter for driving the VGA signals. It's a 10-bit converter from Analog Devices, ADV7122. We have our EPROMs for the fit functions for mapping of the resolutions. We have our low, red, green and blue proms for the lookup tables for the color mapping. And here we have our prom with the control information for the PAL encoding, because that's all state machine based, the video generation schemes here. Here we have a MT5C256. This is the RAM for the frame buffer. And here on top we have a Motorola MC1377. That's a Polar NTSC encoder. It depends on the crystal you connect, 4.43 or 3.58 megahertz for the video standard you would like to support. So they just have to fit the correct crystal up here, and they have to program the correct prom bits here for either video standard. There's the switch, remember, on the back of the camera, switching between NTSC and NTSC PAL and VGA. So when you select the VGA, the composite video output becomes completely rubbish, because now the system is running at the timing special for VGA monitors, and when you switch to PAL or NTSC, on the VGA output, no monitor will lock because it's a lot too slow, the signal which is coming out. So you see, it's just the clocking of a state machine. They switch around here when you select the different outputs. And again, the backside of the board. Oh, okay, here you see it. 2 bulge wires. Yes, they can do it. And I really don't want to remove the focal plane array and all this fancy vacuum glass stuff right here. So I'll try to film that for you by hand and leave it within the housing. So here you can see the front of the unit. It's the focal plane array sensor, output connections here on the glass tube. Again, the heatsink from the Stirling cooler unit and the Stirling cooler hot side piston heatsink right there. I'll try to give you a better view on this unit, so let me just turn the whole unit around. Sorry, it's a little bit shaky right now. So this is the other side of the unit. Remove some connections. Here again, you can see our hot side from the Stirling cooler. I don't know what you can do here, whether that is some kind of fill port or for lubrication or for measurements. That's a heatsink for the hot side too, so this is the whole unit assembly here. Becomes rather warm. Here inside I think is the piston and the voice coil for actuating the Stirling cooler. The unit is filled with helium, I think, as a refrigerant. And inside this unit there is a little cold finger, and that's the actual part which is cooled down to cryogenic temperatures. So let's take a look at the front of the camera. I'll try to show you the focal plane array in more detail. Let's try whether I can bring this into focus. No, it's quite hard. So yeah, here it is. Actually, you can see it. Right down there, the shiny surface, that's the thermal imaging sensor itself, this focal plane array. Some would like a CCD sensor, like I mentioned before. And in front, you see the glass bandpass filter thing mentioned in the manual for only passing the appropriate thermal wavelength around, let's say, 3 micrometer. Well, let's reassemble the unit and hope that it still works. So now comes the moment of truth. Let's see whether it still works or not. I've attached the camera to my laboratory power supply here, 12 volts. And I've attached the VGA connector to my monitor here on the top. I'll show you soon. So let's switch it on, and then you will hear a rather nasty noise from the piston within the Stirling cooler. And when the cryo cooler reaches its temperature, it slows automatically down the Stirling cooler, and then image is displayed. So I'll switch it on, show you the picture by now with a 50mm lens attached to the unit, and then I'll come back in a few minutes and show you the result when it has hopefully reached its temperature and shows the thermal picture here. So let's start. So by now the Stirling cooler has reached its temperature. You can hear it slowing down. So now it's no more cooling down, it's only maintaining the reached temperature at minus 193 degrees Celsius, I guess. So let's try to point this thing to the radiator. Let's switch it to color mode. Try to turn it to something. So here you can see my hand in front of it, and if I get it right, you see it's a rather high resolution, so it's a quite good camera for its age. Again, here in black and white. And here you see the stuck pixels I mentioned before. Inverse mode. And of course, the whole system is 30 FPS. And the nice thing with these, let's shut it down. So you see, now it's drawing about 2.2 amps. And during the cool down phase it's drawing 2.9 amps at 12 volts, so it consumes quite an amount of power. Thanks for watching, feel free to leave any comments down in the comment section, and see you soon in Pryor's lab. Bye!